All right, so yeah, welcome to this video. This is the intention of this video is to talk about the surface code, definitely to review the mathematics, but also to connect it to the physical realization. And in essence, I mean, I want to be thinking about the architecture and the downstream effects of how the quantum error correction, like a surface code, affects the resource distribution and resource estimation downstream. So, I mean, I think maybe a high level diagram that I want to create here has something to do with, first of all, the codes very clearly shape how the computers are going to be built. They're kind of the backbone of the computing device. And this shows up in a pretty extreme case with fusion-based quantum computing because really, if anything, the whole architecture is based on things like decoherence times and other sort of decoherence effects in a quantum system. So the whole architecture is designed around robustness and also code, the ability to implement a code, a quantum error correcting code. Now the point, I'm not going to do a review of quantum error correction from first principles, unfortunately, but I do want to say that the surface code and really whatever choice of quantum error correction code you use has a lot of downstream implications for the rest of the computing architecture. And this, explains that, we have a bunch of math, but this actually gets encoded into physical system. And it's not always straightforward how this gets done, especially because there are so many different physical architectures. So, I mean, in this video, we'll probably focus on the fusion-based quantum computing architecture. But, the goal as a kind of motivation for the whole paper is definitely to have the numerical and quantitative processing side understood, not just the mathematical side. So maybe the title of the video is something more like Surface Codes from Theory to Practice, because, I know I can understand a theoretical description, I think, but what I really want to understand is what's happening to each individual photon, for example. So with that kind of background of the surface code built, the challenge in creating quantum error correction codes lies in finding commuting sets of stabilizers that enable errors to be detected without disturbing the encoded information. So that's a code design criteria, and special code constructions are required to find stabilizers with the desired properties. So this is really, we need like a block diagram view of what a stabilizer code is. So what you specify for stabilizer codes is an error set, and then you have physical qubits. So what does a stabilizer code design do? The stabilizer code, given a set of errors that is characterizing a quantum channel and a set of physical qubits that are resources that you have available, the code is going to produce a stabilizer set that satisfies a number of properties. And that stabilizer set is going to describe a code space. Okay, that's kind of the engineering way to look at it, in my opinion. So let me try to reiterate. Really, there's an error set, and then there's an encoding from lowercase n physical qubits resources to lowercase k encoded qubits. And those k encoded qubits occupy a code space, C. And the stabilizer design problem is essentially to identify this code space. And this code space is chosen in such a way that if you encode information in it, it will produce syndromes for that error set that map back to the error. And that's what allows those errors to be correctable. So there's a number of ways to depict this, but the code design problem is to find stabilizers that anti-commute in unique patterns with the error operators to do. So that's the stabilizer design problem in a nutshell. It has to satisfy these properties that are given in 4.1. So I think that's going to be our review of stabilizer codes. Oh, and then finally at the bottom, we'll say that these would then form the stabilizers of a NKD code, where N is the number of physical qubit, K is the number of logical qubits, and D is the distance of the code. And remember that distance is defined as the minimum number of errors that will change one code word to another. So those are errors on physical qubits. So for example, a distance 3 code If it suffers a weight 3 error, for example, a not gate or an X error rather on 2 qubits and a Z error on another, then, and those actually propagate through the measurement, then that will be distance 3, and that will turn that code word into a different code word, a neighboring code word. So now that we understand what a stabilizer code is, we can start to talk about the surface code. So I think the main motivation that we need to understand is that the stabilizer design problem is very open-ended. So it's hard to find stabilizer codes for a given error model. The mathematics of the code design doesn't respect things like the physical locations of qubits or coupling constraints, or maybe even physical proximity of qubits or lack thereof. This was, I think, the motivation for the surface code, because the surface code has a property that it's basically topological. And a topological code is built up through this process called patching of repeated elements. So what's important here is that it's modular in its construction, and it also has some respect for physical proximity. It respects nearest neighbor, or it upholds nearest neighbor interaction only. So those are two really practical engineering problems. It's hard to get qubits that are far from each other to interact, and obviously engineers like modularity. So the surface code hits both of those. It addresses those in some meaningful way. And so for that reason, it's very useful. It's very clearly a descendant of stabilizer formalism, but it integrates more physical awareness of the architecture than does the purely mathematical stabilizer description and stabilizer code design process. For surface codes, it is beneficial to adopt a pictorial representation of the code qubits in place of the circuit notation that we have used, or that is commonly used for quantum error correcting codes. Figure 7a shows a surface code 4 cycle, the fundamental building block around which surface codes are constructed. The circles in figure 7a represent the code qubits, and the squares represent ancilla qubits. The red edges represent controlled X gates, each controlled on an ancilla qubit A and acting on a data qubit B. Likewise, the blue edges represent controlled Z operations, each controlled by an ancilla qubit and acting on a data qubit. These controlled operations are the gates with which the stabilizers of the 4 cycle are measured. Well, the point is that the 4 cycle designates a code space. An error process acts on the 4 cycle and corrupts the qubits, which are the vertices. And so then we have to measure those qubits to understand what happened and correct. But obviously, what it's saying here is that we're going to measure the ancilla qubits. So we're gonna transform the ancilla qubits by the gate, by the action of the gates, and then we're going to measure those. And those ancilla qubits are then going to carry information about the subspace that the state has collapsed into. So these gates are creating entanglement between the data and the ancillas such that the data can effectively be measured non-destructively. Now, given that ancilla 1 has 2 controlled X operations acting on it, that's going to be measuring the XX stabilizer. And then similarly, ancilla 2 has ZZ, so that's going to have the ZZ stabilizer. That's what it measures. So this is very closely analogous to a Bell measurement. In fact, it's exactly the same thing, because as we know from previous videos, the stabilizers XX and ZZ, not only do they commute with each other, but measuring on those operators is consistent with measuring 2 qubits in the Bell basis. It's very important to highlight the connection between this surface code 4 cycle and the Bell state measurement, especially because we're going to take this to the fusion paradigm where basically the entire architecture is built off of Bell state measurement in an optical setting. But in essence, from a coding perspective, we have 4 physical qubits, and according to this, the number of logical qubits it encodes is equal to 0. Now, the reason for that is because only one subspace is being protected here. So in other words, the code space is one-dimensional, and that code space is 0, 0. However, in conclusion and in connection to scene 2, this is the modular primitive with which we build larger surface codes. And again, maybe the connection to Bell state measurement becomes useful here as well. Okay, so Now we will get into the 512 surface code, which is basically section 5.2 of the paper. So this is a tiling of the 4 cycles into a square lattice. So looking at that figure, by inspection, essentially by reading off the controlled gates that are connecting the data qubits and the ancilla qubits, you can build the stabilizer set that characterizes this code. So we can write the stabilizer based off the diagram and looking at the gates that connect. So that helps us produce, that is essentially the stabilizer group that encodes 1 logical qubit into 5 physical qubits with a distance of 2, or the 512 code. And as you can see, the stabilizers are, either all X or all Z. Now, what we want to emphasize about this code is that it protects against arbitrary single qubit errors. For example, X and Z errors occurring on one of the data qubits. The presence of those errors will trigger non-trivial syndromes in the ancilla measurements. Now, if you look at the qubits on the boundary of this 512 code, you'll see that the top and bottom boundaries are red, and the left and right boundaries are blue. These are considered different types of boundaries. These boundaries actually have a lot to do with the logical operators of the surface code. The logical operators of the surface code can be defined as chains of Pauli operators along the edges of these boundaries. For example, X on 1, X on 4, that happens to correspond to a logical operator because it commutes with all of the stabilizers in the stabilizer group. So in conclusion, we could produce equation 46, which says that the logical X operator for this code is equal to an X applied to the first and fourth data qubit, and a logical Z operator is a Z applied to the first and second data qubit. Because these logical operators have a weight of 2, the distance of the code is 2. So the next section for us to look at is on the scaling behavior. In essence, the distance scales with the size of the lattice. So for distance lambda, equation 47 gives a family of codes which encode a single logical qubit. So this describes how the physical resources scale with the distance of the code. So I think we'll leave things there for now. The purpose of this video, this is the part 1, it was really to motivate why surface codes came to be. And then it motivated, or we introduced the 4-cycle and then the 512 code, which are kind of basic, modular building blocks for the surface code that help you understand how they work. And we also emphasized things like the boundary and the scaling properties of the surface code. Both were very important. So next time we'll kick off on the decoding process so that we can understand why a decoder, how a decoder leverages some of this structure to make that process simpler. And then once we do that, we'll be able to actually maybe try out some decoders ourselves, like maybe implement some decoders, at least in a simulated environment. So yeah, thank you for watching, and I'll see you in the next part.